Hey everyone, today we're going to be dealing with concavity and points of inflection. Up until now, we've been dealing with the first derivative. Last class, we started talking about the second derivative. So let's see what the second derivative can actually tell us. Looking at the graph that's on your page right now, you'll notice certain sections of the graph are concave down, kind of look like a sad face like this, or concave up, and look kind of like a happy face. That's the simplest way of saying it. So if I was to mark the areas where it's concave down here, and it's concave up here and here. Where it changes concavity, so from concave down to concave up, or from concave up to concave down, you have things called points of inflection. So for example, there's one here, there's one here, and there's one here. The way that we mark them is POI, point of inflection. Some people write IP which stands for inflection point. It really doesn't matter to me. I tend to use POI. So a point of inflection, if I was to describe it, is where the concavity changes. And how do I find it? Well, I find it when I set the second derivative equal to 0. It's concave up when the slopes of the tangents are increasing. Otherwise said, the second derivative is greater than 0. It's concave down when the slopes of the tangents are decreasing. Otherwise, f double primed of x, the second derivative, is less than 0. The second derivative has three major roles. The first is to confirm where the maximums and minimum points are. For example, if something is concave down, that means that this point here will be a maximum. If an area is concave up, this means that this point contains a minimum. It helps us test for concavity, just like I said, and then it tells us the difference between stationary and non-stationary points of inflection. Now, this isn't a common topic in the IB, but it is part of certain curriculums. So I'm just going to say the following. If I take the point of inflection and I sub that into the first derivative and I get out 0, the point is stationary, which means it does not move. If I take the point of inflection and I sub it into the first derivative and I don't get 0, i.e. I get anything but 0, positive or negative, that means that the point is non-stationary, which means it moves. So that's the simplest definition of it. It's really about subbing in the point of inflection into the first derivative and seeing what you get out. Now, let's try some examples, shall we? It says here, find the point of inflection and then find the concavity for the following functions. So first take the second derivative. I can't go right to the second derivative. I have to take the first derivative first. So everybody take the first derivative. The first derivative is 3x squared minus 6x plus 4. The second derivative is equal to 6x minus 6. It then says, find the points of inflection, and that's by setting the second derivative equal to 0. Which we already know how to do technically. 6x minus 6 is 0, 6x is 6, so x is equal to 1. This looks very familiar to you, and it should. It's almost identical to finding critical points. This time, instead of using the first derivative, I'm using the second derivative. To test for concavity, I'm again going to make my sign table. Notice I'm using the second derivative information. 1 will go here, 6x minus 6. Pick a number less than 1. 0 is great. That's negative. Pick a number bigger than 1. 5 is great. That's positive. That means this is concave down, and this is concave up because one is negative and the other is positive. Now it says here, state the points of inflection. So the point of inflection is here at 1, something. How do I find the something? Well, I go all the way back up to the top, and I plug it into the original function. When I go and I plug it in, I get 1 minus 3 plus 4 minus 5, which comes out to negative 3. So my point of inflection is 1, negative 3. It tells me whether to figure it out if it's stationary or non-stationary. So take the derivative and plug in 1 into the derivative. When I plug in 1 into the derivative, I get 3 minus 6 plus 4. So 3 minus 6 is minus 3, plus 4 is 1. My answer is 1. This is not equal to 0, therefore the point is non-stationary. And that's really about it. Pretty simple. Try the next example on your own and then check your work. So I take the derivative. F prime of x is equal to 4x cubed minus 24x squared. I take the second derivative. F double prime of x is 12x squared minus 48x. I want to factor and set it equal to 0. So 12x squared minus 48x is equal to 0. I'm going to take out a common factor of 12x. I'm left with x minus 4 in the bracket. X is equal to 0 and x is equal to 4. I'm going to make my sign table now. 0 and 4. I've got 12x and x minus 4. Pick a negative number, so negative, and that's negative. Pick a number between 0 and 4, let's say 2. That's positive and that's negative. Pick a number bigger than 4, 5 or 10 is great. Positive and positive. Negative and a negative. A negative and a negative make a positive. A positive and a negative make a negative. A positive and a positive make a positive. Therefore, this is concave up, concave down, and concave up. I have a point of inflection at 0 something, and I have a point of inflection at 4 something. I'm going to take 0 and unplug it back into the original equation, and I get 0, 0. If I take 4 and I plug it back into the original equation, I get negative 256. And that's it.